Hello again, and welcome to this second part of the video on asymptotes. So it's part 3 of grass sketching and a continuation of asymptotes from last time. So before we go into this, a quick recall perhaps of what has been done. Quick recall. So x equals to a is a vertical asymptote for f of x. If, remember what happens for vertical asymptotes, you need limit as x approaches a of the function not to exist, so d and e. And we also saw that it's possible to have a horizontal asymptote, so y is equal to b is a horizontal asymptote for f of x if this time around it's the limit at infinity, actually at both infinities, plus and minus infinity, and the outcome of this limit should give us b. Okay, so this is what we saw last time. Let's see if we can apply this into the following little example that I have prepared for you. So it's a good 3-star example. Find all vertical asymptotes and horizontal asymptotes. Why not? All vertical asymptotes and horizontal asymptotes for f of x is equal to 2x squared plus 5x minus 3 over, what shall we have, x squared plus 6x plus 9. Let's see how that goes. Let us start with vertical asymptotes, and we'll take a look at horizontal soon after. Okay, so vertical asymptotes. Remember, first of all, you need to find where, first, you need to know where the denominator is equal to 0, because that's actually is going to give you the candidates for, or the ones that are susceptible to be vertical asymptotes. So the denominator to be 0 is going to give you what? X squared plus 6x plus 9 equal to 0. I guess I can certainly factor that into x plus 3 times x plus 3. It is a perfect square trinomial. So this is 0 when x is minus 3. Good. So now, second, I need to find the limit as x approaches negative 3 of my function of 2x squared plus 5x minus 3 over x squared plus 6x plus 9. All right, so it's a good place to mention that these are good limit problems, so we're reviewing what we've seen in the very early part of the semester. So how do we do limits? We actually cheat. Let's replace x by negative 3. 2 times negative 3, 2 times negative 3 squared plus 5 times negative 3 minus 3 over minus 3 squared plus 6 times minus 3 plus 9. What do I get? That's 18 minus 15 minus 3. Uh-oh. That's 9 minus 18 plus 9. Uh-oh. So this is not undefined. 0 over 0 is not undefined. What is it? It's indeterminate. Okay, so we know what it means. It means more work. That's what it means. So let us see if we can figure out the true value of that limit. I know it's not 0 over 0. So let me see. Well, this is certainly something that needs to be factored. So 2x minus 1 and x plus 3 should do the job on top. The bottom, we've already done it before. X plus 3, x plus 3. This goes. And now I find myself with the limit as x approaches minus 3 of 2x minus 1 over x plus 3. I cheat again. 2 times minus 3 minus 1 over minus 3 plus 3. And this time I get confirmation. I get justification. Minus 7 over 0 is actually the answer. That is good for me because when I'm looking for a vertical asymptote, I need the outcome of the limit to be D and E. So confirm. We have x is equal to minus 3 is a vertical asymptote. Great. Okay, so we found the vertical asymptote. Let us now look for the horizontal asymptote for this guy. So we can get rid of this, I guess. And we are now seeking horizontal asymptote. Horizontal asymptote, we're going to take a look at the limit. As x approaches, we're going to begin with infinity because we should be doing plus or minus infinity, right? So limit as x approaches infinity of 2x squared plus 5x minus 3 all over x squared plus 6x plus 9. We cheat and we're going to get clearly infinity over infinity. We know the way out of there, don't we? We divide top and bottom by x to the highest power. The highest power is 2, so why don't we do 2 steps in 1? Every term is going to be divided by x squared. Everywhere I look, it is divided by x squared. So x squared divided by x squared. 6x divided by x squared. 9 divided by x squared. So this is the limit as x approaches infinity of, let's simplify, 2 plus 5 over x minus 3 over x squared, tutti quanti 1 plus 6 over x plus 9 over x squared. Let us cheat. Let us replace x with infinity. It's going to be 2 plus 0 minus 0. Why? Because 5 over infinity goes to 0, 3 over infinity goes to 0, and the same thing for these guys, the same thing for these guys, they all go to 0. So 1 plus 0 plus 0, that's 2 over 1, that's 2. And that means that y is equal to 2 is a horizontal asymptote for the graph of this function. I just want to point out that because this is a polynomial, the top is a polynomial, and the bottom is a polynomial, the minus infinity limit will be the exact same as plus infinity, so I won't do it. So just a remark here, limit as x approaches minus infinity of this function in this example is the same as the limit as x goes to positive infinity. This is a quick remark in this situation only, because we have poly on top and polynomial at the bottom as well. Okay, so that was a good review example on how to find asymptotes. We'll do some more in class. And right now I'd like to introduce you to a summative example of pretty much all the work we've been doing so far. So let me get rid of all of this. And let me propose to you the solving of the following summative example. summative example. Okay, so this is an example that is supposed to bring together to be the sum of so much of the things we have done so far. All right, so what is going to be the statement here? Sketch a graph. Sketch a graph of f of x that satisfies all of the following conditions. That satisfies all of the following conditions. And I'm going to give you all sorts of conditions here, stuff that we have seen before. So what are the conditions that I'm going to give you here? I'm going to say, first of all, f prime of x. F prime of x is actually going to be greater than 0 if x is less than minus 2, and f prime of x is going to be less than 0 if x is greater than minus 2. So I'm giving you some conditions here that pertain to the first derivative. Now, furthermore, I'm going to give you that f prime. Oh, so the second derivative, right? We're going to have to see what this means. The second derivative actually shall be less than 0 if x itself is less than 0, and it's going to be positive if x itself is greater than or equal to 0. I'm also going to tell you that the limit as x approaches 0 of f of x does not exist. That's another piece of information. I'm also going to tell you that the limit as x approaches, what shall we say, what is easier, negative infinity or positive infinity? Let's say positive infinity. Let's give this some sort of value. So you have the value of two limits. And finally, I'm going to give you that the point minus 2, let's say 4, is on the graph of f of x. Is on the graph of f of x. Wow, that is quite a bit of information, right? So let's see if we can sort of decipher this information here. I know that when I have a limit, like here, this actually has to do with information concerning an asymptote. So here we are told that the limit as x approaches 0 does not exist. What does that mean? What does that mean if the limit as x approaches 0 of the function does not exist? It means we have a vertical asymptote here. And here's a limit at infinity. Not minus, but only plus, right? So the limit as x approaches plus infinity of f of x is 1. Those two things are information that pertain to the asymptote. So the first thing I want to say is that there is a vertical asymptote at x is equal to 0 since the limit as x approaches 0 of f of x does not exist. That we are given. I'm also going to say that there is a horizontal asymptote at y equals 1 since we are also given this, the limit as x approaches infinity of f of x is equal to 1. As for the rest, it looks like a bunch of things that I'm not too sure what to do with, right? I got like negative, positive. So I suggest that we kind of organize the information here in a table. I suggest that we actually try to make a table that will give us a chance to interpret the information in a coherent and cohesive way. So from minus infinity to infinity, let us start with f prime. What do we know about f prime? Here, f prime is positive when x is less than minus 2. So why don't I put minus 2 here and say that f prime is positive? That would make sense, right? And we also know that f prime is negative when x is larger than minus 2. So f prime is negative when x is on the right of minus 2. Now, that tells us something about f. Remember that this is where we put the things together. If the first derivative is positive, what does that tell me about the function itself? It tells me that the function itself is increasing, and here it is decreasing. And I can have a little bit of a separation here. Yes? Make sense? So we're organizing all this information here that looks complicated into a table that's going to tell us the real nature of the graph. Now that's not all. I also have information on f prime prime. I also have information on f prime prime. What is the information on f prime prime? F prime prime is negative when I am on the left of 0. So let us have another number here, 0. And let us see that f prime prime is negative when I am on the left of 0. It is also positive when I am on the right of 0. It is also positive when I am on the right of 0. What does that mean if f prime prime is negative? That doesn't have to do with increasing, decreasing, but it has to do with concavity. So this is concave down, and this is concave up. So in a nice little table, one single table for both the first and the second derivative, we have been able to gather the following information. Now, here comes the jewel of this thing. I am yet again going to add a last line to this already well garnished table. I'm going to call this last line the line for the graph. And here's what I want to do with this guy. I really want to separate that from above. And here I have a separation at minus 2. I'll have one here as well. And here I have a separation at 0. So in this last line, we actually merge together all the numbers that they come from f prime or f prime prime. At this point, it doesn't matter. We just put them together in here. Okay, good. Now, here's something super interesting. In this interval, if you focus yourself on minus infinity to minus 2, you are clearly increasing and you are clearly concave down, right? What could this mean? If you're increasing and concave down, which half of this downwards parabola are you if you are increasing? Which half of this parabola are you if you are increasing? You are definitely this, right? Because the other half would be decreasing. So whenever I am increasing and concave down, I know that my graph looks like this. Ain't that sweet? And if I'm decreasing and concave down, then I am here. I am in the second half, if you want, of the parabola, because the first one goes up, the second one goes down. So if these two conditions are met at the same time, my graph will have to look like this. Ain't that swell? And if I'm increasing and concave up, what do I look like? First half or second half? The first half goes down and the second half goes up. So if I'm increasing and concave up, the graph will have to look like this. Finally, If I'm decreasing in concave up, decreasing in concave up, I will have to look like this. Now, please notice that all of these four shapes are all different from one another, right? All of these four shapes basically are very different from one another. They represent a particular format for the graph. So let us take a look at this here. Back to my problem. In this interval here, which corresponds to minus infinity to minus 2, I am increasing and I am concave down. I am increasing and I am concave down. So basically, I have that shape. I should not use red. I have that shape. In this small interval between minus 2 and 0, between minus 2 and 0, what am I? I am decreasing and I'm still concave down. Decreasing, concave down. The shape must look like that. Finally, when I'm here in the last interval 0 to infinity, I am still decreasing, but now I am concave up. I am still decreasing and I am concave up. So I must look like this. Now you know what? These three shapes put together properly in the right place in the Cartesian plane, these three shapes will make the graph of f of x. That's kind of remarkable. Okay, so we'll revisit this technique in the next video when we actually do more of the same sort of thing. But all I want to say is that using this table and the information about the asymptotes, along with one little thing here, that the point minus 2, 4 is on the graph, using asymptote information, point on the graph, table of variation, I can sketch the graph that I want. Oh yeah. All right. So let's do the graph. Let's do it here. Now that we've put all the information into the table, we don't need all this gibberish anymore. Okay, so we're going to give ourselves a Cartesian plane. Here's a y-axis that I'm going to put as a slash, not a slash, but a dot, dot, dot. I'm going to tell you y in a moment, x and y. So now I'm telling you, why did I put this as a dot, dot, dot? Because I remember that x is equal to 0 is a vertical asymptote for that thing. So that's x is equal to 0. It's the y-axis, so dot, dot, dot. Also, another dot, dot, dot at horizontal y is equal to 1. So longer dots just to differentiate the vertical from the horizontal. Y equals to 1 and x is equal to 0. And now, what do? I know the point minus 2, 4 is on my graph. So let's say minus 2, 4 is here. Minus 2, 4 is here. So minus 1 would be here and minus 2 would be there. 4 has to be above this thing here. And now I'm going to basically use the information here to glue that to the graph. So from minus infinity to minus 2, I must actually show this shape. So from minus infinity to minus 2, I'm going to go in blue, minus infinity to minus 2. And then something very strange happens. Yes? What very strange thing happens? I end up crossing a horizontal asymptote. You didn't think that was possible, huh? But it is. It is actually quite possible to cross a horizontal asymptote. What is impossible is to cross a vertical asymptote. Let's continue. So, between minus 2 and 0, now I gotta do this shape. Minus 2 to 0, I gotta do this shape. So I am up here and then I am down there. Notice that I'm getting closer and closer and closer and closer to my vertical asymptote, but not touching it. Finally, from 0 to infinity, I got to do that. But now I got to try to respect my asymptotes. So where do I actually go like this? I don't have to, because basically I need to show something like that. And I'll tell you why in a second. So here I am going up and getting closer and closer to the vertical asymptote. And here, this is where the horizontal asymptote shows up. When x goes very, very far to the right, the y value that I approach is actually 1. So this is actually the shape of the graph. With a local max at -2,4, no local min, and no actual point of inflection because 0 is not part of the domain of the function. So that is a strange graph, yes, I convey, because it actually crosses a horizontal asymptote not once, but twice. And here's another portion. Remember that this, I'm not going to write on my wall, but if I could, I would actually make this taller because it leans towards the vertical asymptote. And to the right, it goes very close also to the horizontal asymptote. So if you're a little overwhelmed by this right now, it's absolutely normal. The first time we actually see this type of exercise, it's a little overwhelming. But after doing 2, 3, 4 of these, things fall in place usually nicely. And that's exactly what we'll do in the next video, where I will present a general strategy for graph sketching. It'll involve everything we've seen together. So there'll be nothing new. We're just going to be putting together a lot of information, organizing it nicely, and be able to sketch quite nice graphs. In the meantime, stay well, be safe.